Yeah.
Shall I keep like this or inside?
Yeah, in like that.
Speak something.
Hello. It's okay? We'll keep it. Huh? Yes. Let me know if you're sitting well.
Just don't use the extreme corner.
Yeah, I cut off.
Yeah,
That one, just whatever.
And
The unimportant part is there.
that font size is good enough.
Yeah, but probably it will reduce. But I hope someone will warn me. Yeah.
But I'm only on the second row, so I'm not a good indicator.
Yeah. Get someone on the. That's okay. Mine is just Yogeshwaran.
Okay.
I don't put my family name.
That makes more sense to me.
Yeah.
Okay, thank you.
Yeah, I'm always fighting with people not to use it.
Okay. Let's start. The second talk of this morning is given by Yogesh on spatial spin systems, please.
Thanks, Anita. And thanks to the organizers for inviting me to this workshop. I think it's the third or fourth Indo-Dutch Indo networks, and been happy to again come here. So this is a joint work with my supervisor Bartek Blazizin and Joe Jukic, and thankful to IFCAM, CNRS, and Submatrix for the funding. I gave a talk, this is part of a general work on CLT for mark point processes. Okay. Two things. At the back, if my font is not visible, please let me know. I will try to write it large, but now and then it will go back small. And please remind me. And I will use some abbreviations. I hope it's clearer. Okay, so there's a general work on central limit theorem for mark point process with Bartek and Joe. I gave a talk on the general theory actually at ICTS last year, and we were really thinking we were going to complete. And then Joe came with saying that something that we could really apply the general theory to spin systems. And we really thought, okay, we could do it quickly. Then it turned out that we needed to extend the theory. And, it really is, I think we are now close to completion. But so instead of explaining the general theory or anything, I will rather focus on illustrating the theory through two examples of spin systems. Okay. So this is what I will be doing. Okay. And one more this thing, I will say that you will see from the talk and the examples, it is something, the moment I was asked to speak at ISI networks or ICTS networks, I'm very sorry. I knew that it had to be on this. Okay, I knew I had to speak on this, and you will see the reasons. No, that was a genuine mistake. Sorry. I hope they can delete it from the recordings and they will invite me in the future. Okay. Should keep my. Okay, so I have a graph to begin with. So the graph is G, where my vertex set is, let's say I have M points in RD. Okay, so I take graphs in RD. I'll use the script G. And again, I will avoid all the generalities and focus only on particular examples. There will be two graphs I'll be considering. So the first graph is what's called the K nearest neighbor graph. Okay, so Xi is a neighbor of Xj. If Xi is among K nearest points of Xj or vice versa. So I put an edge between 2 points. If one of them is among the K nearest to the other, so I put an edge between them. Okay. So this is the graph, and this is a well-studied graph in computational geometry and so on. What one can show in this graph is the max degree is upper bounded by K star. It's some function of D also. It depends on K and D. Okay, depending on the dimension and the parameter K, there is always a maximum bound. So it's a bounded graph. Okay, the degrees are bounded, but the edge lengths can be very long. Okay, so it's bounded degree, but long edges. Yeah, there's no randomness as of now. Huh? Uniform and up to, I mean, unless as long as they're in general position. Okay, so I'll put a little maybe this thing. Okay, that as long as they're in general position, this is a K star. Okay. Okay, and what am I going to consider? So I'll put two models. Okay. So I'll say about two models. Second is spin models. Huh? I think in planar it is 6, and I think it grows linearly in K and dimension D. I think it grows linearly in both. Yeah, D times K with some constant. Essentially, what you have to do is, suppose you have a region like this, you take a point like this, you divide into like 60-degree regions, and you say like, look at, if there are, when do you get K points here? So you cannot have that beyond some this thing, more points cannot lie here. If too many points lie here, beyond k points lie in each region, they will connect to each other and they won't connect to this. So it's like k times the number of 60-degree regions you have to divide into. Okay, 60 or maybe 120, one of the this thing. Okay, so here is the first model, hardcore model. Okay, so I'll be considering sorry about already a notational change, but for convenience, I'll be considering random field indexed. I'll be considering random fields indexed by these vertices. It's a dependent random field, and the values Bx are in a finite set K. Okay, this is finite. And often I will take only 2 examples, which are really, really simple. Okay. First is hardcore, and your K is just 0, 1. And the probability, here comes the randomness, is equal to Vi, 1 less than I less than M. This is proportional to lambda times Vi, product of over I equal 1 to M. And then Vi, Vj is 0. Okay, so it's the usual hardcore model with an activity parameter lambda. That is, whenever a site is occupied, I put a lambda weight proportional. And then I'm looking only over all configurations where no 2 neighboring sites are occupied. Okay, so no 2 neighbors can be 1. Yeah, it is a random field indexed. It's a random field indexed by the points. Labels or marks on these points. And now I'm saying the probability, and this is random. So I'm saying the probability distribution of these marks. I'm giving you the joint distribution. I'm saying it's proportional to lambda times Vi. So it only matters if Vi is 1. And then, and only those Vi's such that no 2 neighbors are 1. Okay. So this is the usual hardcore model on a graph, except that my graph vertices are in space and it's a k nearest neighbor graph. Okay, you can define it on any graph. It's defined on any graph, but for the results I'm going to say later, it's going to be only this graph. Okay, so that's what we're able to. Proportional to lambda. Yeah, lambda to the power. Yeah, thanks. Please. Okay, and second model, since Frank is here, next model I'll do is the Wiedemann-Rawlinson model. Okay. Huh? Yeah? No. Because the points can be spaced anywhere, right? And k equal to 1 means I will map each xi will have an edge to its nearest neighbor. But many other points can get edge to xi because xi may be nearest neighbor of many points. But like I said, it cannot be too many points. Not too many points can have xi as their nearest neighbor. Okay. So Wiedemann-Rawlinson model is K has only 3 states. So these are my 2 examples. Okay, and in this, and I'll put a chi here because it's conditional on the, I've given the points. Very, very similar, but with a slight difference. Uh, 0. No. If 2 points very close to each other cannot be 1, then they will be actually an edge. Yeah, unless there are many points in between them. Then it is possible. Then it is possible. Okay, so this is the Veedham-Rawlinson model. So what does it do? I can be having 2 colors, positive, negative, and nothing. Okay, so there can be no color, but also you can think of it as red, blue, and no color. And what is being avoided here is there can be no red and blue together. Sorry. So I should have put -1. Yeah. Yeah. No opposite colors can be neighbors. Okay, so there can be empty side, but no opposite colors can be neighbors. And again, now there's an activity parameter lambda in which I count only those sites which are colored. So sites which are uncolored are not given any weight. Okay. This is the 2 models. I'll be more or less restricting myself to. And in these 2 models, I'm asking for a very particular property. Okay. So I'll call this. There's a property called weak spatial mixing. Okay. And one time I'm okay. Okay, what does this property weak spatial mixing means? So I have a subset X chi prime, which is in chi prime, and a subset of chi. Okay. And it's the graph boundary. So I look at all the neighbors of chi prime in the graph which are not in chi prime. Okay, so it's the external graph boundary. And in graph distance, I say I have a distance G from chi double prime to the boundary. Okay, so let me draw a figure. So I have this subset chi double prime and a larger set chi prime. Okay, both of these are part of chi. And now I'm saying this distance is at least L. Okay, distance from the inside to the outside boundary is at least L. And the property I'm going to ask is the following. I'm writing the notation in a slightly abbreviated manner and I'll parse it. It's something that's common in Gibbs and spin systems. So what does it mean? This is the conditional distribution of chi double prime given the configuration on the outer boundary. So I'm giving you a particular configuration outside. Let's say it's a valid configuration. So I give you a configuration outside, okay, on the boundary. Anybody who knows me, at some point it will happen. Any time I'm starting with points, the only reason is to make them random eventually. Yeah. So, yeah. Now, what do? I'm saying, but definitely at the first level, this is the first level of randomness, and then we add points, and then that is where the interesting stuff for me. Okay, so I have a configuration V on the boundary, I have a configuration Z on the boundary, and then I'm looking at the conditional distribution in the inside. So both of these are different distributions now. And the point of saying they are weakly spatial mixing is that this has to be exponential a to the power L. Okay, and this condition is what I call as This is what is weak spatial mixing. Okay. So this is not something we introduced. This was introduced by people in spin systems, at least as far as I know. I mean, even in 90s, it was already there. This is the total variation distance, sorry. Z is another boundary condition. So you have one condition V, some values. I put another condition Z with different values. The values could be different. Okay, but I'm saying no matter any two conditions you take, you get two different distributions in the inside. They will have be very close up to this exponential factor. And TV means in total variation distribution, I'm comparing in distribution. Okay, in distribution, these two laws, conditional laws inside are very, very close. Okay, exponentially close. That's the important point. Okay, and A is some constant, but it's universal and, doesn't matter. It's universal for us. And L is for all L. This is true.
So I can understand this condition is basically saying that you don't feel the boundary as much.
Yeah, you don't feel the boundary as much. Okay. Yeah. And again, uniformly over, no matter where you do it in the graph and all that. Okay. Okay. Now, so in general, this need not be true for spin systems or anything. Okay. So this is not an easy property to prove, but it is a very important property to show various things about uniqueness, and of late to have a sampling. When do you get a good sampling algorithm to sample a measure depends on this weak spatial mixing property. Okay. So this is of its own interest, and people have been studying in both computer science and statistical physics and probability. When do spin systems satisfy this property? Okay. So here is the first thing. I'm not going to prove when do spin systems satisfy, but we are going to exploit things which are already in the literature. I think I wrote too big, but I think it's okay. The lambda here okay. So this lambda implies for, give me a hardcore model and take the lambda to be less than k star by k star divided by k star minus 1 into k star minus 1. Why is this ugly looking or it's not too bad. Okay, Piyush is not there, so I can, ugly looking is okay. But this is a result of Sinclair, Srivastava, Piyush Srivastava, Stefankovic and Yang. Okay, they showed that under this assumption, the weak spatial mixing holds for this model. Okay, so this is the partial Indian this thing, and indeed a lot of this thing was, I understood a lot of this thanks to Piyush, who explained me generously a lot of the literature on spin systems and said where things stand. Okay, so this is something they prove, and the proof is firstly by establishing some kind of, like what he pointed out, at two large scales, somehow the boundary effect goes down. So they try to show some decay of correlations in this model by comparing it to a model on a tree, what is called the self-avoiding walk tree. So give me any graph, you look at all the possible self-avoiding walks, you can represent it as a tree, which is called a saw tree. So they compare the decay of correlations on the graph with the decay of correlations on a tree of self-avoiding walks. And as we have already seen in many talks about, some talks about trees, on trees you have nice recursions and a lot of things you could appeal to. So they set up a good recursion on trees and everything, and they do this. Okay, and just to show for this and a slight variant model, but this is very specific to the hardcore model and so on. Okay, and it is indeed not a, I mean, it's not like, now there are extensions to other models and so on, but these are very specific to this kind of models. Okay. So they do it with actually the connective constant. So you replace k star by the connective constant of the graph. So there was an earlier work by Whites, which did it for a bounded degree graph. but Sinclair and Srivastava, Stefankovic-Yang extended it to anything with finite connective constant. Okay, but somehow in random graphs, we are unable to show uniformly the connective constant is finite, and that's why we put this blanket assumption of bounded degree graph. Okay, so their result is more than this, and they also do it for some monomorph dimer model and all that. But it's still very specific to hardcore and some related kind of models. Okay. Wiedemann-Rawlinson, on the other hand, the same thing is true. It's a bit of a here lambda is less than it's on time. I think I'm okay. So now I can tell the detail. In this, at least I can give a better idea of the proof. And this is, here comes the Dutch part. Vandenberg and Mays, sometime in 90s, introduced a technique called the disagreement percolation. Okay, and in fact, they consider the hardcore model Wiedemann-Rawlinson. It's a very general technique to show weak spatial mixing for spin systems. It was a general idea, I think, to Vandenberg, and then Vandenberg and Mays developed it in generality. It will give you a very similar bound even for hardcore without the factor 2. But it works in general. Even without the factor 2, it will give you this bound. But what these people did is for hardcore, you could do it much better. One can see that if you remove 2, this is still smaller than this. Okay. Okay. Mixing. Yeah, both of these conditions ensure weak spatial mixing in these two models. Next, I'll say, yeah. So I want to say, at least in this model, why is this not too hard? So I want to convince that this assumption is not like a, something I'm just cooking up, or it's not like people, you cannot check it. It's possible to check it in reasonable cases. Okay. Okay. So what did the technique of Vandenberg and Mays, the disagreement percolation, what did it do is that what they said is this can be upper bounded. That is, they use a stochastic domination technique, which is also something involved in the work of Sinclair and all. There exists a path PQ is Bernoulli site percolation on G with probability Q, which is in some sense, I'll take it as a sup over X belongs to this. There is another sup here. I have missed sup over X and V and C. Okay. So let's parse this. So what did the result of Vandenberg and Mays is that they control upper bound this total variation distance by existence of a path in a Bernoulli site percolation model. What do I mean by a Bernoulli site percolation? Is that each site in each vertex in the graph is kept open independently with probability Q. Every site I open or close, open with probability Q independent of all the other sites. And in this simple model, they are asking for, is there a path from chi double prime from the inside to the outside? Okay, so you're asking for a path here. I'm asking for a path here. Okay, in this much independent model. The advantage with this compared to this is a very dependent model. Okay, what they are controlling it by existence of a path in a highly independent model. And there is an explicit estimate on the parameter Q, which is in some sense this same total variation but at a single site. I make my chi double prime to be a single site, look at its boundary neighbors, and I estimate this when L is equal to 1 and chi double prime is a singleton. You take L to be 1 and chi double prime to be a singleton. So this is same as L equal to 1 and chi double prime is a singleton. Okay. So you take at a single vertex, you measure this at a single vertex. Yes. Yeah, supremum over all vertices. No. It's over the entire graph. Over the entire graph. Because here I am, I'm not having any more x double prime. I'm telling that I look at x double prime when it is a singleton, and my L is L is 1. So this is the easiest possible thing. And what they are telling is that this, if I know, and then somehow I can recursively do a coupling argument to say that for the effects of boundary to percolate inside, I should have all these sites open with this probability. Okay. Neighbors of x. Okay. So nx, is also same as, I don't know how I'm putting it wrongly, but
what is G here?
A graph, right? I've taken a graph here, the k nearest neighbor graph. I'm always having an underlying graph. Everything is with respect to that graph. And the site percolation is with respect to the graph. The question is here, you are looking at the effect from the boundary to come inside in a very dependent model. And what they are saying is you can dominate it by something in an independent model. And its existence of path in a percolation thing, this is something we always know, and it's increasingly in percolation theory. There are a lot of bounds for studying this site. So using this and a very, very simple, straightforward, like a branching process type argument, you can show this. So you have to estimate Q in different models. It's not always easy. But for example, in the Wiedemann-Rawlinson or hardcore model, I picked these two because in these, the Q can be estimated independent of the graph in some sense.
But typically, you say this works really well because you're in a setting where you have this exponentially. Now this it goes back to the Brushian, it's sort of an iterative thing. Doesn't matter where your points are, and in the exponential case, it should be very good bound.
Right, but in general, you could take a larger, what we are asking is something stronger, not just that it is decaying to 0, but exponential. So I need to take Q a little smaller. I need to get exponential decay here. Okay. But now, like we know from percolation theory that anytime Q is less than some subcritical parameter, this decays exponentially fast. So this is the point that you can exploit with this disagreement percolation. But then in specific models, you can always do better, okay, by using something more according to the model. Okay. Okay, so these are the two spin systems. We will assume the spin system satisfies this assumption. And now, let me still keep this, but now comes the randomness as I have been wanting. Looking at it, I'll take P to be a Poisson process. So it's just IID points thrown on large boxes. Okay, I'm not going to give the full description, but I take P to be a Poisson process, essentially IID points on very large boxes. Or, again, I'm not going to state the general assumption on the point process, but the other example where everything can be verified. I mean, all the theorems stated in more generality with many assumptions for the point process, for the spin system and all that. But in I'm just stating in examples where all can be checked in a more easy manner. Genebre process, it is, okay, so it's among the class of what is known as determinantal point processes, and it is, you take eigenvalue of a n cross n complex Gaussian matrix, let n go to infinity, the limit is the Genebre process. Okay, so this is just to say that Poisson, of course, everybody, it's the IID in the most nicest case, but also to indicate that the results hold in a slight generality beyond Poisson. Okay, in some models which are beyond Poisson. And then Pn is P intersect n. I take a window of volume n. So this is dimension D. Remember, I have points in Rd. So this is dimension D. I take a window of volume n, look at my points falling within this. This is my point process. And then we consider the two models. Okay. So we have two models of spin systems. So I look at the k nearest neighbor graph on Pn, and this is induced spin system induced by k nearest neighbor graph on Pn. So I have a k nearest neighbor graph on Pn. It induces me, let's say, the hardcore model or the Wiedemann-Rawlinson model. Then I have this set of spins. I define Hn to be the sum. No, I don't need the graph to be connected. In some sense, by the model, if it's not connected, it's actually much simpler, because you break into small components and you can handle it more easily. The problem comes is when you have really a giant component or percolation happens, then it's an issue.
They're sort of, and the boundaries are hard, right? You're not making this into a torus.
No. It's I'm not making it into a torus. Okay. So theorem. So this is what we prove. If variance of Hn grows and mu is positive, it grows in n, okay, as a power of n, then oh, sorry. Thank you. And square root of variance converges in distribution to a normal 0, 1. Okay, so this is our result, that given all these ingredients, so what are we saying is that, okay, you give me a spin system which is having this weak spatial mixing, okay, and look at the k nearest neighbor graph, which is the point I'm using. The k nearest neighbor graph is the uniform bound on the degrees. So in principle, if you give me any other graph with a bounded degree, this could still work, or you could control the connective constants uniformly, you could still do it, okay. So actually in both the results, you can replace k star by the connective constant. So this is quite possible. Percolation theory result as well, and as well the other one. And so this is our central limit theorem, that it is telling that, okay, because it's a finite set, I don't have to check any moment conditions. So all it reduces is, at least in these 2 point processes, is to checking a various lower bound. This is non-trivial. I don't say that, okay, it is checkable easily. We do not know in many cases, okay, but believed to be true. It's the sum of the spins. So if I divide by the number, I think it's called empirical magnetization or whatever. Okay. Yeah, Vx, I think of it as a spin. Okay. And I'm looking at the total spins, sum.
It's a random question. Does the Ising model on this graph satisfy this needs?
With some parameter, except that, okay, it's in Vandenberg and Mace, you can see the computation for a lattice. If you want to do the computation for a general graph, you need to have some degree. It will involve all kind of hyperbolic cosine and all that. So yeah, just out of, illustrate the main things, we didn't get into those computations, but it can be computed in Ising model as well.
High temperature, right?
Yes, high temperature. Yeah, indeed. So the lambda is the inverse of the high temperature. So it means if lambda is to be thought of inverse of temperature. So lambda small is meaning temperature is high. Indeed. Of the k nearest neighbor graph. Like I said, all I needed is this degree bound or bound on the connective constant. I get a uniform bound no matter what my point process or realization is on the connective constant. No, it will show up in the variance also. It will show up. But in the sense that, okay, I don't expect this factor to change because of that. The constants will depend. The constants, but not in the exponent. It would be surprising if it were to show up in the exponent.
If there's enough independence in the system, then you get this.
Exactly. That's the point is that this is independent, and then the thing we need from the spin system is this weak spatial mixing.
If the exponential was weaker, then you don't get this.
Faster than any polynomial is okay, but I do not know of really examples where someone has shown something which is any of the methods. Can they give you faster than any polynomial but not exponential is unclear. And it was just convenience in a technical point to forget this in between of faster than polynomial but weaker than exponential. Okay. Yeah, for example, in the proof, stretched exponentials are easy. If you do stretched exponential, it's easy. But if you want to go below that, it's a bit more. High polynomial, it may be possible to push with our methods, but not the optimal kind of. Okay. And it also depends on the variance highly. If you can guarantee me the variance, the factor nu is 1, I can reduce the decay there. There can be a way to do this. Yeah. Yes. Even for Poisson. So our methods don't really distinguish the Poisson versus non-Poisson. So I will give one example in Poisson where you can use the percolation results more better, the more recent ones, and go a little more. So I think one is true is that weak spatial mixing in general will imply uniqueness of the limiting Gibbs measure if you are on infinite. Yeah, because of the graph, if there is a, if you take a k large and the graph percolates, I think lambda large, then you will have a non-uniqueness space. I don't know, it's not explicitly proven, but it's to be expected just by the lattice analogy, because the moment you have some percolation in your underlying graph, then you expect a phase transition in lambda. But if your graph is completely, there's no giant component, then there should be no phase transition. But so this is one thing as an open kind of thing that I do not know in Poisson or point process, these kind of spatial random graphs in any reasonable level has it been established. Okay, I'll keep this, I'll remove this part.
Geometry plays a role to the nearest neighbor.
Yeah, it plays a role only through the nearest neighbor. Okay, so before describing one model where actually degrees are unbounded, but we can still carry out our program in some way, I'll maybe give a idea of the overview of a proof. Not at all going to go into any kind of detail as you would expect, but at least give the rough arguments underlying the proof. So as people realize the weak spatial mixing, you can convert it to something slightly better, is that you can show that the total variation distance of chi prime and chi prime I'm very sorry, there is this ideological, this is too much. That's the cardinality. Very, very stupid. So I'm very sorry, but yeah, if it's almost without this cardinality, it's not possible. Okay, I'm always thinking in singletons in mind, but and what is this? Depending restrict graph to M neighborhood around I prime. So what am I doing is that I'm comparing the spins induced by the original model, and then I look only at a distance M and I forget the graph outside. I look at this induced graph, I get a new spin system because my graph has changed. Okay, I've changed the graph from the original graph to a graph which has only distance M away from each of the chi double prime. And now I'm comparing these two. So this implies that from weak spatial mixing, what you can deduce is that this also can be controlled in the exponentially in M. Okay, so the graph beyond a distance M, the relevance decays fast enough. And now, then using the property of k nearest graph and the point process, and the next step from this is, which is really a reasonable jump. This is where I'm going to be more, is to translate this into something, and I'll put an abbreviated notation. Be a bit careful, but this decays some, I don't know, AP e to the minus AP R. Or I think this is not visible, so I wrote on the wrong side. Okay, let's parse this, and this is the key thing, and F is a bounded Lipschitz function. F is a function bounded by 1, Lipschitz in 1. Okay, what am I saying? I'm looking at the joint distribution at P many points of the point process. Okay, I'm looking at the joint distribution of P many points, and the expectation have to be some conditional expectations suitably. So this is a subnodal, simplification to say this is a vector, okay, at x1 to xp, and I'm looking at the same by restricting my point process. So what are we doing? This is in the graph distance, this is in the Euclidean distance. So I'm translating this total variation bound on the graph distance to a bound. This is essentially like a Wasserstein bound, Wasserstein distance with respect to the Euclidean distance. Okay, so now I go from graph to Euclidean. Okay, so this was essentially in technical sense, what took us some time was that this was good enough to prove the central limit theorem. Earlier, we had a version of such stabilization with the modulus inside and all bounded functions and kind of things. We had a much stronger kind of a notion of stabilization. Okay, this is called, we call it BL stabilization. And from this, one can prove a CLT for the point process. How? It's in 2 steps. First, you prove that these local restrictions have a decorrelation property, that if you restrict it locally, these spins are local functions of the statistics and these decorrelate. And then using this stabilization, you extend the decorrelation to this. And there's an entire machinery using, we call it again, it's just using decorrelations with respect to bounded Lipschitz functions. And you can control the cumulants and use the cumulant method to get a CLT. Okay, so from this, you can first show that the cumulants of this do not grow too badly. Then you can try to use this to show that this one doesn't grow too badly, the cumulants. And once the cumulants do not grow badly, normalizing by the variance, what we need is, we assume this because you normalize the cumulant by the variance and it will go cumulants, high cumulants will go to 0. This is a reasonably well established machinery the moment you can get decorrelations. Okay, and this thing is somehow to deduce up to this stage, and this used 2 things. One is the weak spatial mixing was very much key. Okay, and how much time? I think I have about 5 minutes.
So I guess for this simplification, right, on the it's you also use some properties of your random graph.
And the point process.
And the point process. So how, to what extent do you think that can generalize beyond, say, K nearest neighbor?
So you can look at something like, so there are 2 ingredients. So if you have this property, this to this requires much weaker on the random graph, in the sense that you need your random graph does not have too many, cannot have a long edge with very high probability. The probability of long edges in a random graph should decay exponentially in the distance, stretched exponential, all kind of things is okay. But the main reason we use the K nearest and bounded degree is to get this, because in a uniform sense. So, okay, there was an argument between me, all of us, that should we state in a more general fashion the result, but only in 1 or 2 examples we can really check the uniformity at the moment, and we were unhappy with stating this and then cheating people at the end. Okay. The most difficult thing still is weak spatial mixing. It's the weak spatial mixing. Yeah. So there are other examples of models where we don't need so much, and then we could do it on more general random graphs. Okay. And the point process also can be a little more general than these 2 examples. No, it should be maybe possible, but the point is that, let's say that I'll give one example where we slightly relax the weak spatial mixing to weak spatial mixing with high probability. Okay. I mean, our methods are very much with handling cumulants, showing cumulants go to 0, and these are essentially tailored to Gaussian. If you want non-Gaussian, I'm unclear how to do it. Okay. Where do I erase? I'll probably erase this part and look at the I'll take a Poisson process now. I'll now only consider Poisson process. And my graph G is xi is a neighbor of xj if xi minus xj is less than equal to 1. It's Poisson process and parameter is rho. I have a parameter rho, okay, intensity of the Poisson process. I look at the graph which is known as the Gilbert graph or the random geometric graph, one of the most common graphs. The edges here are local, but the degree can be unbounded. Potentially the degree here can be unbounded. So it's an unbounded degree graph, but the edges are somewhat local. Okay, and what is known in this is that there is an intensity rho c. This is the percolation threshold. So I'm not going to go in. So there is an intensity rho c. If rho is greater than rho c, the graph has an infinite component. If not, the graph has only finite components. Okay, and one can take PC to be minimum of rho divided by rho c comma 1. Okay, and then use the method of disagreement percolation to show that I can take lambda less than PC. Okay, in all my parameters, yes, it's important to remember that I'll take lambda in 0, 1. Okay, so if I take lambda is less than PC, then weak spatial mixing for hardcore, and in the other one I have to take 2 lambda less than PC, implies weak spatial mixing. So I have to be a bit careful here. Weak spatial mixing with high probability for hardcore, and in the Wiedemann-Rawlinson also with a high probability for Wiedemann-Rawlinson. Okay, I don't know if yeah, exactly. Thanks. So with high probability here is with respect to the location of the points. Okay, I can show this with high probability. So it won't hold for all Pn, but as you can see from the proof technique, the point I need is this, that if I can show this with high probability, and that is good enough to do this. Okay, so there is at least one case where we could see this, but we are unable to really push it to some kind of a general this thing, because specific models, this kind of the way to quantify the high probability keeps changing. Okay, so we don't have a very general kind of thing to say weak spatial mixing with high probability. It needs some quantification that is missing. But what is definitely possible, it's answering this question of generality. It may be possible that in other models also, that if one can somehow establish this with a high probability. Okay, and that is sufficient to prove this, and then the rest of the machinery will go through. Yeah. No. Yeah. So when you talk, if you are in Poisson, there are ways to get a lower bound, but the, in non-Poisson, really, it's hard to say. Even much simpler things. So in general, that's like in the subject or this thing, there's always this condition lurking around, and in any complicated statistic, it's much harder to check. Okay. Not verified, but I think it should be okay. Okay, I think that's about it. Or do I have anything in mind? Okay, so I think I'll stop here and I'll take any questions. Yeah, thanks.
So Yogesh, if you take your Wiedemann-Rawlinson model and you project out one of your colors,
Yes.
then what does it look like? Then it becomes a thing with that looks at some sort of volume, and
does that model still have your mixing conditions?
I think weak spatial mixing should go well under projecting it.
Okay.
I think because you are, I mean, I'm saying for these laws itself.
Mhm.
So if you project, it should be accounted in the total variation distance, right? You are taking, in some sense, supremum over a
Because
total
it's very
variation.
uniform. Okay.
Yeah.
Okay. Yeah.
So can you also generalize this to the case where the spins not vary in a finite set and maybe in a compact interval or something?
It should be a little more possible, but some implications like this were much, I mean, some of the things like using some point Hammersley Clifford or things like that, you could use more crudely with finite sets, gave us some constants to play more easily. I think I'm a bit worried on compact at some points. I have to think, but we got stuck at some places to do it easily. Yeah.
Any more questions? Doesn't seem to be the case, so let's thank Yogesh again. A coffee break, and we meet at 12 o'clock.
Inside, I'm already involved.